In the name of God, hello dear students of grade 11. Welcome back to Thinkable Physics YouTube channel. My name is Masood, and we are going to complete our study about the capacitor. In previous lessons, we talked about the capacitor and we got some information. We talked about the general form of the capacitance. C is equal to Q over delta V. We talked about how to charge the capacitor. We talked about the actually structure of parallel plate capacitor. And right now we are going to explain one more subject, which is measuring capacitance in vacuum. How do you measure the capacitance of a capacitor in a vacuum? By the way, what's the meaning of measuring capacitance in a vacuum? It means you have a parallel plate capacitor, and there is no dielectric between these plates. So there is an empty space. There's a vacuum between two parallel plates. This is called a vacuum capacitor. And our textbook mentions only this type of capacitance. It only mentions parallel plates capacitor in a vacuum, or vacuum capacitor, not dielectric capacitor, right? Let me read the rule dedicated for this type of capacitor. The rule says C is equal to epsilon naught A per D. Epsilon naught A over D is used to measure capacitance of a parallel plate in a vacuum. So what does epsilon naught stand for? It's a constant. Epsilon naught is a constant, and it's equivalent to the what? 8.85 times 10 to the negative 12 coulomb square per Newton meter square. And it's called permittivity of vacuum. This is the constant, right? This is a constant. I give you this number in the exam. You just actually substitute it. It's a constant. A represents area between two plates and is measured in meters squared. A represents actually area between two plates, right? Let me draw for example, capacitor. For example, this is a parallel plate capacitor. The area between them, this area, actually is A. The area between two plates, we name it as A, and separation or distance from plate to plate is called D, right? So there are factors. A is measured in meters squared, area between two plates, and separation between two plates actually is measured in meters. A is measured in meters squared, and D measured in actually D is measured in meters only, right? I want to actually ask you some question before I read the question. We have this law, right? The law says C is equal to epsilon naught A over D, right? Think about the relation between C and A, right? Both of the C and A are in numerator in the equation. So there must be a directly proportional relationship between C and A. I mean, the more the area of the capacitor, right, the more the capacitance is. One more factor. This is the first factor. I'm gonna discuss another factor with you. So we have the same law. We talked about the relation between C and A. Right now, take a look at C and D. So where do you find them actually? Where are they located in the equation? One is located in numerator and the other in denominator. So there must be actually inversely proportional relationship between C and D. I mean, the less the distance between two plates, the more the capacitance is. Let me write another actually write the first relationship between C, and I want you to be with me, hit me, which actually relationship is there between C and A. We said that because C and A are in numerator, that's why there must be a direct relationship between them. The more the area, the more the capacitance. Here, the less the area, the less the distance, the less the separation, the more the capacitance. Right. I want you to solve this, answer these questions for me. I'm not gonna actually answer them. Answer this question and comment them after you watch the video. Right. So we have 3 questions. Just actually read them and circle them. Circle the answers. I'm not gonna answer. Let's move on to the other actually to the other substance, measuring capacitance for spherical capacitor. So if we have parallel plate capacitor, we have this rule: C is equal to epsilon naught A over D, right? But if you have a spherical capacitor, the rule changes, right? The factor changes, the rule changes. What's the rule? The rule is here. For a spherical capacitor, we use this law. C is equal to R over Kc. What is R? What is Kc? Let's read it. C is equal to R over Kc is measured to capacitance for a spherical capacitor. And you know that a spherical capacitor consists of 2 concentric spheres, 2 concentric actually conductor spheres that wrapped about each other, right? And there's a vacuum, there's an empty space between them. This is called actually a spherical capacitor. R stands for radius of a sphere and determines the size of the capacitor. You know that if you take a look at the circle, actually, this sphere has a particular radius, right? This sphere has a particular radius. Why do we say R stands for radius and size? Why do we say radius stands for size as well? Think about another sphere, actually a smaller sphere. Actually, I wanted to determine the size of the sphere. Determines the radius of a sphere. And right now I want you to compare between the radius of either circle or either sphere. So I can say the less the radius, the less the size. The more the radius, the more the size. Right? One more factor. Kc is equal to 1 over epsilon naught, and it's a constant actually. This constant is called Coulomb constant. You are familiar with this constant. We got it in chapter 6. In Coulomb's law, we got it. Coulomb constant, and it's measured in Newton meter square over second square over Coulomb square. I want you to be very accurate because Kc is reciprocal to the epsilon naught. That's why their units are opposite as well, right? So you must be very accurate to determine which is which, to recognize the unit for either, because units are completely opposite, right? I'm gonna prove this equation for you after reading the last information. The last information says capacitance of any capacitor, whether it's parallel or spherical, depends on 2 factors. So irrespective of type of the capacitor, capacitance depends on 2 things. Depends on size and shape, right? These factors are common between all of the capacitors, right? Between all of the capacitors, size and shape. I'm gonna actually prove this equation for you. Let me use the whiteboard. So let me remind you about the general form of the capacitor. general form of the capacitor, C is equal to Q over delta V, right? This is the general form of the capacitance. What do you say about, for example, capacitance for what? Capacitance for, I want you to think about, let me write them actually. So C is equal to Q over delta V. This is the general form of the actually capacitance. Another rule, I want you to think about delta V. What is the rule of what's the rule of potential difference? In actually chapter 6, we got information about the potential difference for spherical, for charges, for point charge. Actually, we got this information, right? For actually electron, for proton, for spherical charges, we can use this equation, delta V is equal to Kc over what? Kcq over R. But in chapter 6, actually, we used Q small. It doesn't matter whether you use Q capital or Q small. It doesn't matter. Symbols are arbitrary. If you are satisfied with Q capital, write Q capital for charge. If you are actually satisfied with Q small, no problem, write Q small. So it's arbitrary. You are not supposed to use Q capital for every equation, as you like. So right now, I want you to substitute delta V in the above equation. So I'm gonna substitute the value of delta V in the first equation. Let's do it. Q, I'm gonna write the Q, and I put a denominator of 1 for Q. Write the value of delta V. Delta V is equal to Kc Q over what? Over R, right? So cross multiply the equation. I want you to cross multiply the equation, or actually not cross multiply. I want you to divide the first fraction over the other. So numerator of the first equation multiplied by the denominator of the second one. What do I mean by this? Actually, far factor multiplied by far factor. Far factor with far factor. Actually, near with near. Near, actually, figure multiplied by near factor. So what do you get? C is equal to, let me complete it here. Actually, I can say C is equal to, this is the last form. You have to multiply R with Q. It will be QR over what? QR over KC, KCQ, right? QR over KC. So because Q is existed in numerator and denominator, you can actually cancel it out, and the last form will take what? The last form of the equation will take, actually R will take this form. Let me actually, the last form will take, the last form of the equation will be R over Kc. And this is our actually objective. This is our goal. So C is equal to R over Kc. It's dedicated for what? This equation is dedicated for capacitance of a sphere, right? And I want you to find the relation between capacitance and radius. So in this equation, you can say the more the radius, the more the capacitance, or the more the size of the capacitor, the more the capacitance of the capacitor, right? So there's a direct relationship between size of the capacitor and actually capacitance. When you are gonna have a, let's say, high capacitance, you have to increase the size of the capacitor. You have to bring a actually large sphere for this purpose. Let's get back to the text. And this is about actually this subject, and I included some questions. I wanted to answer them, read them carefully and answer them, and comment them actually after the video for me to make sure you understand the subject. According to this equation, C depends on which of the following factors. Write them, actually read them carefully, and answer them for me. Question number 2. Space is the general form of capacitance formula. General form. Which one is general form? Right? For what? For capacitance. Let me highlight it for you. So, which rule represents actually the general form? General form of the what? General form of the capacitance. This one. General form. Question number 3. Capacitance of a parallel plate capacitor is measured. Parallel plate. C for parallel plate. Which rule represents C for parallel plate? Question number 4. Capacitance of a spherical capacitor. A spherical capacitor. So we have 3 forms, right? General form, C is equal to whatever. I'm not going to reveal it. Parallel plate has its own actually rule, and a spherical capacitor has its own rule. So we have 3 forms. We have 3 forms for capacitance, or for C. C for parallel plate, C for general form, for actually for all types of capacitor, and C for spherical capacitor. Right. Actually, I included actually a note, and I included a tip, and I told you in advance that using Q small or Q capital is arbitrary, it's optional, as you like. For example, if you like to use actually Q small, use Q small. If you want to use Q capital for charge, actually use Q capital as you wish. I'm gonna discuss these questions with you. Question number 5. Comment on this relationship. And I explained it for you in advance. Actually, during my explanation, I told you about this information. But right now, I'm gonna actually read them. It says comment on this relationship. C of a sphere is directly proportional to the R. What does it mean? It means the more the size of the capacitor, the more the capacitance is. Or the more the radius, the more the capacitance is. Right? Question number 6. Explain why is Earth often used as a reference point for measuring potential differences or voltage in electrical circuits. Actually, Earth is considered, in some situations, we can actually use the Earth as a spherical capacitor. It's actually enormous spherical capacitor with a huge radius, right? Why? Because Earth actually during a thunderstorm, when lightning actually directed toward the Earth, infinite number of charges actually hit the Earth, and the Earth can accept these charges without changing its voltage. That's why it collects all of the charges. That's why we consider the Earth a huge capacitor. It accepts infinite number of charges, collecting charges. And this is the function of capacitor. In previous lesson, we talked about the function of capacitor. We said that the main function of capacitor is collecting energy in the form of charge. And Earth does this actually. During thunderstorm, actually Earth accepts these these infinite number of charges. And that's why we, and by the way, I told you, actually, it accepts actually these high voltages without changing its voltage. That's why Earth will be what? Will be a reference point for measuring the voltage in our electrical circuits. Let me read the answer for you. It says because Earth is so large, it's an enormous, spherical capacitor. It has an extremely large capacitance, you see. Therefore, it can provide or accept. Provide means it can lose. It can lose or gain. Provide or accept means lose or gain. It can provide or accept large amount of charge without changing its electrical potential, without changing its voltage, in other words. That's all, guys, for today. Thank you very much for watching this video, and bye-bye.